Good afternoon, everybody. I'm just going to wait for the rest of the registered delegates to arrive and then we'll commence. Good afternoon, everybody, and welcome to the first in a series of 4 webinars from the Catalyst project. My name is John Booth, and I'm the project lead for Green IT Amsterdam, and I'll be your host for the entire series. Our project coordinator is currently on holiday, but he has recorded an introduction and overview to the project, and we'll start with that in a moment, followed by our colleagues at the Technical University of Cluj-Napoca in Romania with another pre-recorded video on the DC Manager. We'll close with some questions after that video.
Hi, I'm Diego Arnone. I'm a project manager and I'm a senior member of the Research and Development Laboratory of the Engineering Group. And in the role of coordinator of the Catalyst project, I'm going to give you a bird's eye view of this research initiative co-funded by the H2020 Framework Program. This introduction explains at a very high level what the project has developed and what kind of benefits it aims to achieve. Let's start from a proposal. Well, we are in the context of data centers connected to more commodity networks like power grid, data networks, district heating. The proposed idea is that data centers can and should offer energy flexibility services to their smart grid and district heating networks. So data centers should not be considered as only as energy consumers, but as active players that are able to sell their intrinsic flexibility. This is the identity card of the project. We have close to 3 million euros assigned to a consortium of 10 partners based in 6 European countries. 3 of them are industrial partners, the coordinator engineering, Singular Logic and Schubert Phyllis. 2 are small medium enterprises, PowerOps and Carnot. 2 are research institutes, PSNC in Poland and University of Cluj-Napoca in Romania. 2 are utilities, NLX and Oleander. We have 4 data centers that are our workbench for the validation. In the Catalyst vision, data centers are to be intended as multi-carrier hubs that work at the crossroad of more networks, energy networks, and data networks. And these hubs can exploit and manage their intrinsic redundancy to provide flexibility, to deliver system-level multi-carrier flexibility services. The consequent new revenue streams can allow them to invest in energy efficiency and in reducing data centers' environmental footprint. This figure depicts the concept of the project. A data center, thanks to an innovative resource management and optimization system, is able to sell flexibility to the local DSO, the distribution system operator, by putting offers on a local balancing marketplace in order to sell or buy energy, both electricity and heat, in another marketplace, or to move IT workload from a data center to another federated one. Uh, we must think that a data center consumes energy to supply servers that execute workload and generate waste heat. So power, heat, IT workload are strictly linked to each other in a data center. These commodities can be traded in a multi-flavor coupled marketplace that Catalyst proposes as a service. The flavors are electric flexibility, electricity, then energy, heat, IT workload. And this picture shows how a data center stays in the middle. So, in conclusion, electricity, heat, and IT workload are considered as commodities that can be traded, exchanged, transferred in the corresponding emerging markets, either individually or combined to achieve synergies whenever possible. In order to achieve its own objectives, Catalyst has not started from scratch, but this project has merged, evolved, extended, and also integrated the results coming from Geyser and Dolphin, two FP7 research projects successfully completed by some of the partners involved in Catalyst. The new developed tools can utilize and trade the waste data center heat to lower the overall system-level energy distribution footprint, reduce data center energy costs and create new data center incomes, can assess resiliency of energy supply and flexibility, trading off data center assets against local distributed RES, energy storage, and efficiency, can deliver energy flexibility services to the surrounding energy grids ecosystems, can also exploit migration of traceable ICT workload among federated data centers, matching the IT workload demands with time-varying on-site RES surplus availability, or where heat generation is needed. This is the follow the energy approach. These tools have been developed to be adaptable to a variety of data centers categories. Different types, colocation, enterprise, HPC, different geographical location, different architecture, from large centralized to fully decentralized micro data centers. As already mentioned, Catalyst is validating the main results of the project in 4 different pilots. The green geothermal co-location data center in Ponza Martin in Italy, owned and managed by the engineering group, the coordinator of the project. HPC data center based in Poznan, Poland, partially supplied by renewable energy sources that is experimenting the reuse of waste heat by heating up a building of the nearby university campus. A fully distributed data center operated by Carnot, where servers are installed in different buildings as heaters. A co-location data center owned and managed by Schubert Phillips, integrated with a smart grid. They are experimenting the provision of electrical flexibility to the grid. There's also a legacy data center operated by Singular Logic, but used only for lab experimentation. Okay, this card shows the list of the core features of Catalyst that are being validated. So free air and water cooling, geothermal and passive water cooling connecting to the drinking water grid. The first one is tested in the engineering Ponza Martin data center. The second one in Schubert Phillips, the Netherlands, in collaboration with Oleander. Waste heat regeneration via heat pumps and reuse of smart thermal low temperature district heating networks. This is happening in Schubert Phillips and Poznan. Also space heating cooling of co-location data center offices in favorable seasons. So Ponza Martin co-location data center in alpine climate area in Italy, but also Poznan and Schubert Phillips. Smart waste heat reuse and preheating diesel engines and UPS systems, so Schubert Phillips, the Netherlands. And RES, basically photovoltaic panels, and DES, basically batteries, integration, and this in Poznan. Heat demand driven IT workload balancing in a fully distributed data center. This is the case of Carnot in France. Energy flexibility services via backup generator. So battery storage, UPS, and flexible workload adaptation of IT workload. And this is happening in Poznan and Schubert Phillips. IT load balancing, targeting lowering of energy consumption and cooling needs between legacy commercial data centers belonging to different administrative domains, for example, Singular Logic, and green data centers, so engineering Ponza Martin data center or Poznan. Last but not least, the value proposition. There's a nice picture shows the benefits for data centers because this technology reduces the operating costs for energy, is able to improve performance and creates new revenues by reusing waste heat and by providing flexibility services. The energy sector, because we have a better stability and security of supply, easy access to local flexibility services, accelerated heat reuse, but also for smart cities, especially by empowering energy prosumers and unlocking their flexibility potential. So, we need interested partners, people interested in this new idea of data center to be intended as active player in the smart energy infrastructure of the future. So become the catalyst to energy transition, support green data centers in Europe, join the Green Data Center Stakeholder Group. What you need to know is in our manifesto that can be downloaded from the website. And this is how you can join us. That's all from my side. I hope that this short introduction will be useful for a better understanding of all the tools that have been developed and will be explained in the followings. So, enjoy your webinar. Goodbye.
Thank you, Diego, for that overview of the project. And now on to the DC Manager video. This is also pre-recorded, and I'd like to advise that it does have a robotic voice. The video lasts for about 30 minutes or so, and when it's finished, we'll open the door for some questions. So here we go.
Hello. I will present today some of the technical aspects behind Catalyst Data Center Flexibility Management and Optimization. In Catalyst, we are aiming to transform the data centers in active energy players that are operated at the crossroad of electrical, thermal, and data networks, and to leverage onto their internal electrical and thermal flexibility to provide energy services to the local grid. In this way, the data centers will not only contribute to the local energy grid resilience and decrease their carbon footprint, but they will gain new revenue streams on the top of the provided services not foreseen before. To make this vision possible, a model-based predictive control and optimization solution has been developed, and, in the rest of this presentation, we aim to provide details on its main parts: the DC electrical and thermal flexibility modeling, electrical and thermal energy prediction, and, finally, DC energy flexibility management and optimization. We had developed a mathematical model for representing the operation and energy flexibility of complex systems, leveraging on system of systems engineering methodology. The data centers, as large-scale prosumers, represent a good example of system of systems, due to the complex mesh of interconnected components that must operate seamlessly, the IT resources composed of servers and network elements, cooling systems, power supply, and storage systems. Our objective was to model the electrical energy flexibility of various DC components to estimate the DC flexibility availability and to allow DC to provide flexibility services in local grids. Figure on the right shows the model developed to conduct data-driven simulations for estimating the DC energy demand baseline and energy flexibility potential, and for supporting the predictive control of DC operation. It features a graph of atomic systems connected by energy links. The atomic systems are either energy generation and distribution components or energy consumption components. They are connected by links showing the energy transfer between them. Each subsystem has a set of control variables that determines the actions that can be executed to gain energy flexibility. Electrical energy flexibility potential of each subsystem is modeled using mathematical functions. For an individual DC subsystem, we had constructed a formal model, then we had addressed their integration and interconnection in complex systems. A DC subsystem is represented by a tuple featuring a set of inputs, a set of outputs, a set of independent real or integer control variables, a vector of system internal states, and a time model. The behavior of the subsystem is defined by two functions, a transfer function f, and a state function g. The transfer function f computes the outputs of the system based on the inputs, control signals, and state, while the state function g updates the internal state. The control variables are associated with a set of control actions changing the system behavior. Additionally, we modeled the concepts of discrete and continuous time, the complex system's flexibility and adaptability. In terms of flexibility actions and control variables associated to the DC subsystems, the following have been considered. Time shifting of delay-tolerant workload, in the same DC or in other DC. In this case, we differentiate between real-time workload, which has stringent requirements on real-time execution, and delay-tolerant workload, which can be executed anytime until a given deadline. the DC energy demand is reduced at a timestamp with the amount of energy needed to execute the delay-tolerant load that is shifted at a future timestamp, while the DC energy demand at a future timestamp is increased with the amount of energy needed to execute the shifted delay-tolerant load. Dynamic usage of non-electrical cooling systems is used to pre-cool the DC and to compensate the electrical one. At a timestamp, the thermal energy storage is charged, its coolant, such as water-based thermal tanks, is overcooled by using the electrical cooling at higher capacity, resulting in an increased energy demand. At a future timestamp, the thermal energy storage is discharged, the DC is cooled down using the pre-cooled coolant, and the electrical cooling is used at low intensity, resulting in a decrease of DC energy demand. Finally, for batteries usage, the DC energy demand is reduced at a timestamp by the amount of energy discharged from batteries and increased at a future timestamp by the amount of energy charged in batteries. In case of thermal energy flexibility, we have modeled the thermal processes inside the DC to estimate the heat flexibility and thermal inertia, and to increase, as much as possible, the quality of reuse waste heat in nearby neighborhoods. In the figure we can see the system of systems model considered in our approach. When an air-cooled DC uses heat pumps to dynamically generate thermal energy for heating purposes, the server room is used as a thermal energy buffer that allows increasing or decreasing the heat produced. This is achieved by modifying the temperature set points in the server room and deploying and executing more workload on the IT servers to allow thermal energy to accumulate. This will also improve the efficiency of the heat pump operation, which operates better at higher temperatures. The heat pump transfers the heat absorbed from the DC server room to the thermal grid by using a refrigerant-based cycle and 2 water tanks. The cold water tank contains water at low temperatures, which is circulated through the radiator pipe system to cool the radiator, while the hot water tank contains water at higher temperatures feasible to be distributed and reused in local neighborhoods. A compressor is used to increase the quality of heat while being transferred from the cold water tank to the hot water tank. Thus, the thermal flexibility actions considered are to plan the delay-tolerant workload execution to obtain a high server's utilization ratio, allowing to increase, for limited time interval, the temperature set points in the server room while being careful not to endanger the proper operation of IT equipment. As a result, the heat is accumulating in the server room. Increase/decrease water flow rate between radiators and the cold water tank. Varying the flow rate of the water circulating through the radiator pipe system, it can compensate/adjust the usage intensity of the electrical cooling system from the server room. Vary the water flow rate between the heat pump and the cold and hot water tanks. As a result, the thermal energy is transferred between the cold water tank and hot water tank, while a refrigerant cycle is used to increase/decrease the water temperature while consuming electrical energy. Using electrical energy, the quality of the thermal energy stored in the hot water tank is increased. For example, hot water can be reused at around 70 to 80 degrees Celsius. However, increasing the server room temperature set points can lead to potentially disastrous situations, such as equipment overheating and malfunctioning due to hotspot formation in certain areas of the server room. To avoid these risks, before making any decisions, a simulation should be performed to validate the new temperature set points and workload distribution of the IT servers, eliminating the risks of hotspot formation and equipment malfunction. Our solution is to use methods that are based on computational fluid dynamics, which feature numerical simulations to compute the flow of fluids in an area defined by boundary surfaces, which is in our case the server room. For electrical energy predictions, we have considered both the forecasting of demand and of flexibility at different time and subsystem scale granularities, such as day-ahead or intraday. We have developed an ensemble-based DC energy prediction model that aggregates the prediction outcomes of individual neural network-based weak learners to forecast the DC energy demand and their potential energy flexibility. The architecture of our approach can be seen on the bottom of the slide. We have chosen neural networks due to their ability in modeling complex nonlinear processes such as the energy exchange processes occurring inside a DC. At the same time, the ensemble-based predictors seem to perform significantly better compared to individual algorithms for time series prediction tasks. The output of the weak learners is combined using a weighted average to improve the final prediction result. Each individual neural network, which is displayed on the top right of the slide, is generically modeled as a set of neurons distributed over several hidden layers trying to map the energy inputs to outputs through a nonlinear function. Each model is then configured according to the forecasting time window, being fed with historical energy data and additionally with contextual features, and will predict several future energy values. The energy flexibility of a DC measures the potential of adapting its energy demand in relation to a calculated baseline by shifting energy and, as a result, increasing or decreasing its energy demand profile. The baseline energy consumption is an estimate of the electricity that would have been consumed by each DC individual subsystem, or by the entire DC in the absence of any flexibility provisioning optimization. The baseline energy consumption profiling uses similar time scales as the energy demand forecasting process, but it is fundamentally different as it must satisfy both consumers and utility sides, and it is used only to measure the performance of the DC participation into a demand response program. To determine the baseline at subsystem level, we have used the X of Y method that calculates the baseline using the energy consumption data of Y previous days, out of which the most significant X days are selected. The average model middle selects X days with the average load, excluding both the highest and the lowest loads, if they are isolated events. In this way, the baseline is much more stable, and the error, with respect to the load, is reduced, but in this case, the actual energy demand may exceed the baseline at times. Considering the calculated baseline, we aim to forecast the DC energy flexibility for the day-ahead and intraday time frames. To estimate the degree in which the DC can increase or decrease the load in a demand response program using its internal latent flexibility, and to measure the adaptation during the program in a time interval, we have used the adaptability power curve metric defined in the context of the European Smart City Cluster. This metric computes the Manhattan distance between the actual and baseline energy profile vectors and normalizes it using the total power demand over the demand response program time interval. The adaptability power curve metric is defined for each DC subsystem and for the entire DC. We have evaluated the performance of the implemented energy prediction model for forecasting the DC energy demand considering both day-ahead and intraday forecasting time horizons. Each neural network model has been configured according to the energy features of the DC subsystems and to the time frame for which the prediction must be computed, as presented in the table. Analyzing the DC energy demand and flexibility patterns of various DC, we have selected the IT servers and cooling subsystems, which are the major contributors to the DC total energy demand, as relevant subsystems for the energy forecasting process, as shown in the model architecture. There is a strong dependency between the energy demand and flexibility potential of the IT servers and cooling subsystems, which needs to be captured in the prediction model. If the IT server's subsystem has a higher energy demand, it will generate more heat and more cooling will be needed to maintain the temperature set points, generating an increase of energy demand from the cooling subsystem. The obtained results are promising. The first chart shows the energy demand predictions for day-ahead and intraday models plotted against the actual monitored data at a 10-minute sampling rate over the fourth day of test data. Table on the top of the slide presents the prediction results for the DC electrical energy consumption of the IT servers and cooling subsystem. During this test day, the mean absolute error between the day-ahead forecast result and the monitored data is 191.42, while the mean absolute error between the intraday and the monitored data is 179.42, meaning that on average, the prediction is better with about 277 kWh of energy. The flexibility forecasting techniques were evaluated to predict the energy flexibility above and below curves, for the 4 days of test data. The figure below shows the results obtained for assessing the flexibility above the baseline over the test period. The prediction has a 6.81% mean absolute error, the predicted values following closely the real values. These values are colored in orange while the baseline is depicted in green. In case of thermal energy flexibility forecasting, the computational fluid dynamics-based simulation methods have limitations. Calculations related to a single scenario require a parallel environment and a significant amount of time. Performing such simulations for multiple scenarios for every server room in a large-scale data center is costly and time-consuming, being an approach that cannot be considered as affordable and effective in near real time. Thus, to overcome such limitations, we have combined the computational fluid dynamics-based simulations with neural networks-based methods to predict the temperature distribution in the server room, aiming to increase the amount of heat recovered. In this case, the simulations result of numerous configurations of the single simplified setup constitutes the training data set for the neural network-based prediction process, which will be used at runtime for decision making. Computational fluid dynamics simulations of a virtual server room are used to model the input cold air in terms of pumped airflow and temperature, as well as the generated hot air and heat distribution in the server room model for multiple setups. The server room is modeled considering its size as well as the racks deployed in it. The racks are considered as fully and homogeneously occupied with servers. Their geometry is simplified in a way that each of the racks is treated as a single airflow and heat source. They are provided with one inlet and one outlet each, allowing the use of less computationally expensive mesh. Temperature values were acquired by using virtual probes. The input parameters of the computational fluid dynamics simulations are varied to generate different scenarios, each running over an interval to compute the temperatures for the virtual probes. The generated data are fed to a neural network-based infrastructure with the goal of predicting the heat distribution in the server room and the temperature of the generated hot air. The forecasting infrastructure is based on neural networks of type multi-layer perceptron featuring 4 fully connected layers of neurons of type rectified linear units. In this slide we show the obtained heat prediction results in a case study in Poznan Pilot DC. We had varied the 5 input parameters of the computational fluid dynamics simulation to generate 3,125 different scenarios, each scenario being run over a period of 600 seconds to compute the temperatures for the 14 probes at each second, thus generating 8,400 output values. We had chosen to split the main dataset into 60 sub-datasets, each used to train the neural networks-based algorithm to predict the 14 outputs of the simulation for every second of a 10 seconds time interval within the 600 seconds prediction interval. In total, we created 60 datasets for each scenario, that will be used to train 60 multilayer perceptron neural networks. Thus, for each second within each 10-second simulation interval, we created 3,125 training pairs, associating the parameters of each simulation with the output to be predicted at a given timestamp in the future. We train the defined multilayer perceptron-based prediction infrastructure by splitting the data set in 90% training data and 10% test data. As it can be seen from the table, the predictions exhibit an error of less than 0.1 that corresponds to less than 1 degree Celsius, being suited for real-time temperature evaluation to avoid hot spots. The temperature evolution prediction compared with the one generated by the computational fluid dynamics simulations can be seen in the figure on the right for one of the scenarios run. The red lines represent the predicted values while the blue lines represent the real temperature values taken from the simulation. As it can be seen for the sample probes, even for the worst mean square error, the predicted temperature profile follows closely the real temperature profile, exhibiting errors of roughly 1 degree Celsius. The goal of DC flexibility management and optimization is to plan the DC operation such that the latent energy flexibility is shifted in time to meet different objectives of the local smart grid. Here we can see some examples of flexibility services a DC may provide to the local smart grid by using our defined techniques. The congestion management service implies the reduction of DC energy demand profile during the service time interval by managing its operation so that a specific amount of flexible energy is shifted later in time. Load scheduling implies the increase of DC energy profile during the service time interval by postponing the execution of some tasks and altering its profile prior to the service time. We had approached the flexibility management problem by modeling the DC as a discrete system and defining the energy demand of each DC's component, and of the entire DC as a whole, at a timestamp as a function of previous power demand states at other timestamps. At each timestamp, the optimal operation of the DC's components needs to be determined together with the amount of aggregated energy to be shifted in time, such that the DC adapted energy profile matches the flexibility request curve provided as goal. Thus, the optimization objective is to determine the amount of flexible energy of each DC component to be shifted in time such that the DC adapted energy consumption curve follows as close as possible the flexibility request curve. As a result, the distance between the two curves is minimized. This is an NP-hard optimization problem which we had modeled as a combinatorial problem on top of the system of systems modeling approach of flexibility that was presented before. In this figure we present an overview of the optimization problem and the variables considered by the implemented optimization process. Using a simulation of the DC flexibility model, each point representing a system-level control variable in the flexibility control space is translated into an associated flexibility value in the flexibility adaptation space. The adaptability capability is represented by the green point from the control space that is mapped by means of simulation to the green output point from the output space, which represents the adapted energy profile of the DC, as a result of flexibility shifting, which is closest to the flexibility request point colored in blue. In this slide we can see the architecture of the developed DC flexibility management and optimization tool. It takes as inputs the thermal and electrical energy predictions determined by the electricity and heat demand response prediction components, as well as the DC system of systems flexibility model describing the operation of the main DC subsystems. Its main output is the optimal flexibility shifting action plan, such the DC energy profile is adapted to provide various services in the electrical energy, heat, and energy flexibility marketplaces. The energy efficiency metrics calculator is responsible for computing indicators that are associated with the optimization action plan that will reflect the efficiency of its implementation, such as the potential carbon savings, cost savings, amount of energy shifted, etc. The DC operator console displays the relevant information for facilitating the DC operator decision making, such as the electrical and thermal energy production/consumption/flexibility predictions on custom charts for the whole DC or major subsystems, on all time granularities, and DC optimization actions plans to facilitate their validation and simulation. In the table we show the values of the weights used to configure the different DC optimization strategies. We have evaluated the Catalyst DC optimization engine capabilities for managing and shifting flexibility to deliver electrical flexibility services, heat, or combinations of the two. The workload relocation and or hosting to from other DC has been considered as a potential source of extra energy flexibility which can be activated deactivate on demand. In scenario number 1, the flexibility optimization action plan allows the DC to modify its forecasted energy demand to lower the operational costs by consuming less energy when the price on the electricity marketplace is higher, by leveraging on the flexibility mechanisms for shifting energy to time intervals when the energy price is low. The figure on the right shows the electrical energy profile of the DC after executing the optimization action plan computed by shifting delay-tolerant workload from time periods when the energy price was high, hours 10 to 16, to time intervals when energy price is low, hours 17 to 21. By enforcing the optimization plan, the DC operational cost with energy, considering the energy price variation, represented by the purple line in the figure for 24 hours, is reduced with approximately 1.24%. In scenario number 2, the flexibility optimization action plan allows the DC to modify its forecasted energy demand to follow accurately a flexibility order signal curve. As can be seen in the left figure on the bottom, the flexibility order signal to which the DC should respond by increasing the energy demand, is in the interval between hours 16 to 21. Executing the flexibility optimization plan, the DC will deliver the expected flexibility by postponing some of the delay-tolerant workload in the response interval, as can be seen in the figure on the bottom right. Prior to the flexibility service interval, the DC is lowering its energy demand below the baseline, see intervals between hours 2 to 4, due to the shift of flexible energy. In scenario number 3, the flexibility optimization action plan allows the DC to leverage on workload relocation and or hosting to from other DC to further increase its thermal and electrical energy flexibility and, as a result, to increase the revenue streams from selling thermal energy while taking advantage of the low electricity prices in the energy marketplace. The DC uses workload temporary shifting as flexibility mechanism to decrease the energy demand during the time interval 1 to 7 when the energy price is high, and shifting the workload to the interval 8 to 17, when the energy price is low, as can be seen in the figure on the top left of the slide. At the same time, due to a high heat demand in the same interval, the DC can sell its excess heat generation and gain additional profit, see figure on the top right of the slide. Finally, in scenario number 4, we show how the DC operation is optimized to provide energy flexibility services and, at the same time, to sell heat in the heat market. The DC uses its internal flexibility mechanisms, such as delay-tolerant workload shifting, as well as workload hosting from other DC to increase its energy demand to match the flexibility request signal, see figure on the bottom left. Also, because the internal workload is not enough, the optimizer computes an action plan involving workload hosting from partner DC to increase the energy demand by 100 kWh. Figure on the bottom right shows how the DC increases its thermal energy generation during the interval between hours 16 and 21. About 500 kWh workload is hosted over that period to generate an excess heat of around 150 kWh needed to satisfy the high thermal energy demand. Thank you for your attention.
Well, that was a very in-depth overview of the Catalyst DC Manager. And I'm now going to open the floor to anybody that wants to ask a question. We do have some of the consortium members online and available to take your questions. So if you could either go unmute and ask a question or use the question pane that you have. We do have a question from Dick, who basically said, I did answer this earlier, with the very serious COVID-19 crisis delay or even hopefully encourage green data centers over the next few years. And that was from Dick Wallace at Position Systems in the UK. I did answer to Dick earlier. I think if anything, it's going to accelerate it. We've seen a vast increase in the amount of technology deployed during the crisis. And this has started to get some organizations that are active in the data center market to become very focused on their energy consumption and their sustainability, greenness of their operations. All to the good, I'm thinking. So we have got quite a long time left in the webinar for questions. So if anybody has any questions, please let us know. Okay, so not that many questions coming in from the floor. Okay, so I'll close the webinar now then, unless I see anybody raise their hand or ask a question. But we have another 3 webinars scheduled over the next 3 weeks. Next week, it's the Catalyst Marketplace. And this is an overview of the Catalyst software that relates to the market to offer energy flexibility, waste heat, and the migration of IT loads between the Catalyst federated data centers that the presentation spoke about just at the last section there. And that's on the 5th of August. On the 12th of August, we'll have the 3rd webinar, and that's all about our Catalyst pilots, the technology employed, and the provisional results. And I know that we're still testing some of the scenarios, so that would be very interesting. And then finally, on the 19th of August, we'll be covering the Green Data Center Assessment Tool and the Green Data Center Roadmap. We look forward to seeing you again. Thank you very much and have a great afternoon. And before you go, feel free to contact us on Catalyst info at Catalyst projectcatalyst.eu if you have any questions, or the contact forms shown on the previous webinar from Diego. And I'll close it there then. Thank you very much. Thanks for listening.